Okay, in the last session, we discussed about some of the important activation functions used in the neural network. There were threshold activation function, logistic regression or sigmoid activation function, rectified linear unit or ReLU, then hyperbolic tangent or tanh activation function. We also saw the mathematical equation representing these various activation functions. Now we are going to discuss about another important activation function, which is called the softmax activation function. The softmax activation function actually generalizes the sigmoid activation function so that we can classify a set of objects into multiple classes, and these classes need to be mutually exclusive also. Then, so softmax activation function is used for a multi-class classification problem. It outputs a vector of probabilities summing to 1. Mathematically, the softmax activation function is given by the equation softmax of zi is equal to e raised to zi by sigma j is equal to 1 to n e raised to zj. So let's see what is each term corresponds to. So this is the diagrammatic representation of a neural network, which consists of the input layer and output layer. The input layer consists of two neurons. That means the feature vector consists of two values. We are providing two features, x1 and x2, and the output layer consists of three neurons. That means we are trying to classify the given set of objects into three different classes, and the output of each neuron in the output layer will give a probability showing showing how much chance is there for the inputs to be belonging to a particular class. So here we can see that the first neuron in the output layer is represented by this a node, and what are the inputs that are coming to it? It is the weighted sum of x1 and x2. So that means w11 x1 plus w21 x2 plus the bias term that is associated with it. So z1 is actually equal to w11 x1 plus w21 x2 plus b1. And similarly, the second neuron, the input that is coming to the second neuron is represented by z2, and it is given it can be shown as, it will be equal to w, what is the term that is coming here, w12 plus w12 into x1 plus w22 into x2 plus the bias term. Similarly, the input that is coming to the third neuron in the output layer, that is z3, is given as z3 is equal to w13 into x1 plus w23 into x2 plus this bias term, that is b3. So this z1 is the weighted sum of the inputs that is coming to that neuron plus the bias associated with it. Similarly, z2 is the weighted sum of the inputs that is coming to that particular neuron plus the bias term associated with it. Similarly, z3 is the weighted sum of the inputs that is coming to that neuron plus the bias term associated with it. So we can say that zi is actually the weighted sum of the inputs plus the bias term that is associated with that particular neuron in the output layer. Now suppose the values that is corresponding to the inputs and the weights and the bias be given by these matrices. So x1 is equal to 1, 2, and the weights that are coming to, or the weight matrix that is coming to the first neuron, let it be 0.2 and 0.8, and the bias associated with it be 0.5. In that case, we can say that z1 it is equal to 0.2 into 1 plus 0.8 into 2 plus 0.5. So see, that is 0.1 into 2 plus see, it is 0.2 into 1 plus 0.8 into 2 plus 0.5. So that means it is 0.2 into 1 plus 0.8 into 2 plus the bias term associated with it. Similarly, what is the weight vector that is coming to the second neuron? Value of the weight vector coming to the second neuron, it is 0.6 and 0.4. So, and the bias term associated with it is 0.1. So, what will be the input that is coming to it, or z2? Z2 will be equal to 0.6 into 1 plus 0.4 into 2 plus this 0.1. See, 0.6 into 1 plus 0.4 into 2 plus 0.1, that is equal to 1.5. Similarly, what is the value of the weight terms that is coming to the third neuron in the output layer? It is 0.5 and 0.7. So the Z3 will be equal to 0.5 into 1 plus 0.7 into 2 plus this bias term, and that is 0.3. So that value happened to be equal to 2.1. So Z1 is equal to 2.3, Z2 is equal to 1.5, and Z3 is equal to 2.2. So we got all the Zi's. Z1 is we got the value of Z1, Z2 and Z3. Now what is the softmax function? It is e raised to Zi plus the sum of all the Zi's. That is, from, if we have 3 classes, then we have to find out the sum of e raised to Zi's. So e raised to Z1, it is equal to e raised to 2.3, that is 9.974 approximately. Then e raised to Z2 means e raised to 1.5, because this is the value that we got. For Z2 it is 1.5 we got. So e raised to Z2 will be equal to e raised to 1.5, that is 4.481. Now e raised to Z3 will be e raised to 2.2, that is 9.025. So these are the individual e raised to Zi terms that we got. Then sum of all these, what the denominator is actually corresponding to the sum of all these e raised to Zj's. So that means 9.974 plus 4.481 plus 9.025, that is 23.48. So in order to find the softmax function, we have to first find out the sum of all these Zj's. Then that has to be put in the denominator term. No? So for softmax of Z1 equal to e raised to 2.31. Where we get this 2.31? Actually Z1 was 2.3. So it is softmax of Z1 is equal to e raised to 2.3 by 23.48. Where we got this 23.48? It is actually the sum. The denominator term is the sum of all these e raised to Zj's. No? So the sum of all the e raised to Zj's is 23.48. So we got that is approximately equal to 0.425. Similarly, when we calculated the softmax of Z2 e raised to 1.5 by 23.48, we got 0.191. Softmax of Z3 is, we got it at 0.384. So these are the probability distribution that we got for the three neurons. So the output of the 3 neurons is corresponding to this matrix. So what does this mean? This means that the output from the first neuron is having a higher probability. No? So the inputs that we have provided is has a higher chance to be belonging to the first class rather than the other 2 classes. So that is the interpretation we get. So the class 1 has the highest probability, making it the most likely class. Means given the inputs, the features of that are given is more likely to be in the class 1 rather than in class 2 or class 3. That is the interpretation we get. So the softmax also ensures that the probability sum up to 1. So when we get the sum of all the probability distributions, we get it up to as 1. Now, what is the difference between this logistic regression or sigmoid function and softmax function? The sigmoid function is mainly used for 2-class classification. That means the output layer can have only a single neuron when we are using a sigmoid activation function. Whereas the output layer, if we want to classify an object to different classes, more than 2 classes, we have to use a softmax activation function. So the sigmoid activation function shows how given an input x, what is the probability that this x belongs to a particular class 1. Okay, now it can also be, we said that sigmoid function can be used in binary classification. That means if we get the probability of a particular class, then what is the probability of that input belonging to the other class? That is 1 minus the probability that we got for the first class. So the sigmoid function, at most we can have we can use it for a binary classification, that is 2 classes. But if we want to classify an object for more than two classes, we have to use a softmax activation function. That is, the softmax activation function says what is the probability of a particular input X to be belonging to class 1, class 2 or class 3. So because for each of the neuron in the output layer, we will get a probability distribution, and based on the value of that probability distribution, we can assign whether the input belongs to a class 1, class 2 or class 3. We will be, if the class 1 has higher probability, we say that the given input has a higher chance to be belonging to class 1. Whereas if class 3 has a higher probability, means we can say that given the input, these inputs are more likely to be belonging to class 3. Okay. Now we can look at single layer feed forward neural network for binary input. For binary input, we can have a single neuron in the output layer, and so single layer feed forward neural network means we have only an input layer and output layer. No hidden layers are present. That is called the single layer feed forward neural network. So the input layer means it is simply passing the inputs that we are getting to the neuron in the next layer. Since it happened to be a single layer feed forward neural network, we have only a one output layer, and no hidden layers are present. So whatever be the input that are coming, it will be passed to the output layer. So this is a diagrammatic representation of single layer feed forward neural network. Now we can have single layer feed forward neural network for multiple classes. So here what happens, in the output layer we can have more than one neuron. That means if we want to classify an object to three different classes, we have to have three different neurons in the output layer. And since it is a single layer feed forward neural network, there is no hidden layers. All the inputs that are coming will be passed to the neurons in the output layer with weights and bias associated with it. Okay. Now, if you look at what are the descriptions of single layer perceptron, the single layer perceptron is a type of neural network that consists of a single layer of output nodes connected to a layer of input nodes, and it is the simplest form of feed forward neural network. Each input is multiplied by a weight, and the weighted sum is passed through an activation function. Typically it can be a step function or a sigmoid function, and sigmoid function, otherwise it is also known as logistic regression function. Then single layer perceptron can only solve problems that are linearly separable, such as and or logical problems is a typical examples that single layer perceptrons can solve. Now, if the single layer neural network is used for binary classification, then the output layer typically has only one node if we are using a sigmoid activation function. But if we are using a softmax activation function, then it can have two nodes. Okay. Now, if the output layer has more than two nodes, then it is typically used for multi-class classification, where each node represents a probability of a specific class. In this case, the output will use softmax activation function to convert the raw scores into probability across the different classes. So, if for binary classification, we can have a single node at the output layer if we are using a sigmoid activation function, and but if we are using a softmax activation function, even for binary classification, we need to have two nodes in the output layer, and more than two nodes means it is a multi-class classification. So there we can use only the softmax activation function. So this is a diagrammatic representation of multi-layer perceptrons. So here, this is not inner layer, this is input layer. Okay, the multi-layer perceptron, same as in the case of single layer perceptron, we have input layers as well as output layers. But in between the input layers and output layers, we have so many hidden layers also. So, multi-layer perceptron is a type of artificial neural network that consists of multiple layers of neurons, including an input layer, one or more hidden layers, and an output layer. It is a feed-forward neural network that can model complex and non-linear relationships. Then the input layer receives the raw data. The hidden layers, what are the functions of the hidden layer? The hidden layer performs intermediate computations, allowing the network to learn complex representations of the data. Then the output layer produces the final result, which can be used for tasks such as classification or regression. So let's see how this multi-layer perceptron is used to capture the complex data. So let's look at a simple example of XOR function. So see, when we know that in an XOR function, the output will be 0 when both the inputs have the same value. So when x1 and x2 are 0, the output is 0. Similarly, when x1 and x2 are 1, the output is 0. But when the inputs are different, the inputs have different values, then the output is equal to 1. Okay, now we are plotting this in a two-dimensional space. So what happens? The output is plotted against x1 and x2. So we can see that when x1 and x2 are both 0, the output is 0 here. When x1 is 0, and x2 is 1, then what is the output we have? We have an output of 1. Similarly, when x1 is 1 and x2 is 0, we have an output of 1. And when x1 and x2 both are 1, when x1 and x2 both are 1, what happens? The output is 0. So if we try to classify the outputs, we can see that we cannot have a single line to categorize these outputs, because we cannot draw a single line to categorize the outputs. At least we need two separate lines to categorize these outputs, because we can see that all the outputs that are coming between these lines will be of one category, and those comes outside these lines are of another category. So that means by a single separating line we cannot categorize these outputs. So what we do is that we will be using intermediate neurons to capture this non-linearity. So first what we are doing is that when given x1 and x2, we will be performing an OR function on x1 and x2. So and then we will be performing a NAND function on x1 and x2. Then finally what we do is that we will be on the next layer, in the intermediate layer, first we will be doing an OR function, and in the intermediate layer we will be performing a NAND function, and in the next intermediate layer we will be performing an AND function of the inputs or the using the inputs that we obtained as using the outputs that we obtained in the intermediate calculations. So here, in order to perform an XOR function, first we will be doing an OR function of x1 and x2. So OR function of x1 and x2, we get these values. These are represented as an intermediate values h1. Then we will be performing a NAND function. NAND function means x1 dot x2 whole complement, no? So that will be equal to a x1 complement plus x2 complement. So actually we are performing a NAND function. Then we get the intermediate value h2. So that is also plotted. Then what happens? We will be performing a AND function of h1 and h2. AND function of h1 and h2. Then we get values which is actually corresponding to the XOR values here. Okay. This is the output that we get. And h1 is represent. So if we plot this, we get h1 and h2 are plotted here. Then when h1 and h2, when h1 is 0 and h2 is 1, h1 is 0 and h2 is 1, we get an output of 0. Then when h1 and h2 are both 1, we get an output of 1. That is plotted here. When h1 is 1 and h2 is 0, we get an output of 0. So this is the diagrammatic representation that we get when we are trying to plot the values of h1 and h2. That is the intermediate results that we got. Then we can have a straight line separating the separating these two categories of outputs that we got. So actually what we are doing is that we cannot have a single separating line for an XOR function to categorize the outputs. So in the intermediate level we are using an OR function and NAND function. The outputs of OR and NAND are passed to an AND function. Then we get a single separating linearly separable line. So that is the representation power of multi-layer perceptrons. So that means the hidden layers is capable of capturing the complex representations of the data and allowing them to have a linearly separable line after that. So multi-layer perceptrons, each neuron in a layer is connected to every neuron in the next layer, forming a fully connected architecture. The weights of the connections and activation functions determine how data flows through the network. Each layer's output becomes the input to the next layer, and the network can learn non-linear decision boundaries. That's important. Then next, we can look at the representational power of neural network. What do you mean by this representational power of neural network? Actually, it refers to the ability of the neural network to model and approximate complex functions or patterns. So what are the key factors that contribute to this power? There are several factors that contribute to this representational power of the neural network. The first one can be non-linearity of the activation functions. So if we are using non-linear activation functions like ReLU, sigmoid, tanh, or softmax, they have the ability to approximate non-linear functions. So non-linear functions allow the network to learn complex patterns in the data and represent a wider variety of functions. Then next, the depth of the layers. The number of hidden layers is a critical factor. So the deeper the networks are capable of learning hierarchical representations where each layer builds on the features learned by the previous layer. Then next, the third one is the width of the neural network. That means the number of neurons per layer. That is called the width of the neural network. So the number of neurons in each layer also contribute to the ability to capture diverse patterns and features. So theoretically it is said that more neurons per layer allow the network to model more complex relationships. Then next important factor that contribute to the representational power of neural networks is the training data and generalization. If we have adequate number of or sufficient number of samples to train the neural network, it is said that the neural network can generalize well to the unseen data, thus thereby avoiding overfitting and thus improving the representational ability of the neural network. So when we are training a neural network, especially when you are training a complex neural network, we must have adequate number of samples to train. Otherwise the model that we develop may be not producing good results with the unseen data, that is the test data. It may be prone to overfitting. Now another factor that increases the representational power of neural network, or that is critical in increasing the representational power of neural network, is the optimization algorithms that we choose. So we can choose various optimization algorithms like gradient descent, ADAM, RMS, probe, etc. All these we will be discussing in later sessions, and these also impacts the ability of the neural network to find the optimal set of weights that represents the underlying patterns in the data. And the correct choice of the optimization algorithm allows the neural network to converge to a good solution in a faster pace with better performance, enhancing its representational power. Then another important factor that is contributing to the representational power of neural network is the regularization techniques. Various regularization techniques like dropout, L2 regularization, early stopping method, all these can prevent the network from overfitting by constraining its capacity and forcing it to learn more robust representations. Then another important theorem that states that a neural network with at least one hidden layer and non-linear activation functions and a sufficient number of neurons can approximate any continuous function to arbitrary precision. So that theorem is called the universal approximation theorem. It states that the neural network must have at least one hidden layer and it should have a non-linear activation function. It should have sufficient number of neurons. Then that type of neural networks can approximate any continuous function to arbitrary precision. Then next, another important factor that is contributing to the representational power of neural network is the model architecture itself. That is what is the number of connections between the different layers. whether the architecture is a fully connected network, whether it is convolutional neural network or recurrent neural network, all these factors, all these architectural factors contribute to the representational power of neural network. So we can see that different architectures are suited for different types of data and tasks. So we can see that for image data, convolutional neural networks are more suitable, whereas for sequential data, recurrent neural networks are suitable. Thus, a well-designed architecture can significantly enhance the neural network's representational power. Okay, thank you.